So, every Boolean function has size just 2 raised to n times n, and the proof is simply by express all possible inputs and their output using the gates. And you can see that this is just 2 raised to n times a constant multiple. Okay, it is not even square of this. It's very close to 2 raised to n. It's much below 2 raised to 2n. And so that is easy. What is open is are there functions that actually require this much of size, and simple functions. Okay, so that is the lower bound question. The lower bound question is, does there exist an explicit family of functions Fn such that size of these functions is 2 raised to n. Okay, so that is the lower bound question, and depending on how explicit you want, how natural the function should be, these are usually open questions. Okay, if you don't put this restriction of explicitness or natural function, then we can actually show a result. So, fact is about non-explicit lower bound. So, non-explicit lower bound can be actually obtained easily. So, you can show that there exist Boolean function Fn on n bit input such that size of Fn is 2 raised to n by n. So, we can show that in fact, we can show that almost if you just pick Boolean functions in a random way. So, almost all the Boolean functions they do require size to the order of 2 raised to n, and to be precise, the size required is more than 2 raised to n by n. But then we cannot say anything about the explicitness. Okay, so this is why this is a non-explicit lower bound. The idea is just by counting. Proof by counting. So, usually we refer to these kind of proofs as proofs by counting. So, here we will actually count circuits and we will count functions, and we will try to set a mismatch. So, the number of Boolean functions this is essentially, in fact, it is exactly equal to 2 raised to 2 raised to n. Right? There are 2 raised to n input strings, and you can fix their values in 2 ways. So, it is 2 raised to 2 raised to n. Now, let S be the size parameter What is the number of circuits? So, the number of sizes circuits is it basically depends on number of sizes graphs, right. So, you have these no internal nodes and then you want to connect them by wires. So, you can show that it is at most S to the S. Okay, so, work this out as an exercise, that by looking at the graph and you can counting these graphs, you will get a number smaller than S to the S. So, which means that let us fix this S to the S, the number of circuits, to be less than the number of Boolean functions, which is 2 raised to 2 raised to n. So, we can fix S to be 2 raised to n by S. So, we can pick, I mean, we basically want S log S to be less than 2 raised to n. So, we can pick S to be slightly smaller than 2 raised to n. 2 raised to n will not work, but 2 raised to n by n will work, and that is 2 raised to n by S by n, right. So, 2 raised to n by n will satisfy this property, and what this means is then there exists this function with size that can't be computed by any of these size 2 raised to n by n circuits. Right. So, the functions are more, circuits are less, and hence you can find a function which requires size more than 2 raised to n by n. But the problem, I mean, it's a simple proof, but it doesn't tell you how to find this Fn. Okay, it is not. I mean, Fn exists, but it doesn't give a construction. So, it only shows existence. This counting argument doesn't give an explicit Fn. That is the problem with such proofs, but at least you know that if hard functions exist, and in fact this 2 raised to 2 raised to n is so much bigger than S raised to S that almost all functions are hard. But it shows that almost all functions are hard. In the space of functions, almost everything is hard. Very few things are actually have small circuits. Okay. So we have proved two results, simple observations: the upper bound of 2 raised to n times n and the lower bound of 2 raised to n by n. And using this, we already can give a hierarchy theorem for circuits. So non-uniform hierarchy theorem. So let t and t prime be functions such that t prime n So these are functions, obviously we want them to be non-negative valued on natural numbers, such that t prime n is bigger than t. Okay, so as n grows, you want t prime to be bigger than t times log t. Then the set of problems which are solvable by size t prime circuits is strictly bigger. Okay, so I haven't defined it, let me define it here. So this is the set of problems such that L has size Tn circuit for n bit inputs and for all n. Okay, so that's the definition of size Tn. So size of T is a complexity class which is modeled using circuits. So these are basically decision problems which have size T of n circuit, Boolean circuit on n input on n bit inputs. So this circuit family is there. So maybe I should call it circuit family. Okay, and what we are claiming here is that using the above two observations, upper bound and lower bound, we can actually show that for a slightly larger size, circuit size, you can solve more problems. Okay, so size T prime contains more problems than size T if T prime is slightly bigger than T. So this can be compared to, for example, the time hierarchy, right? This is similar to the Turing machine time hierarchy, but has a much simpler proof. So what is the proof? Let's do that. Um, so the idea will be to use these upper bounds and lower bounds that we just showed. So we have shown that so number one, every function has size circuit size less than equal to. So let me change the notation. Let me call this on L. So every L bit, every function on L bit inputs has size at most 2 raised to L times L. And second is that there exists such a function GL of size more than 2 raised to L by L. Right. So we have these two. So first is the upper bound result, second is the lower bound result. So we can combine these two to prove the statement we want, which is size t prime is more than size t. How? We basically have to show a function that is in size Tn but not in the right hand side, right? So let's pick L suitably based on T and T prime. So let's define L such that, sorry, this is 2 raised to L by L. That's what we had shown, right? 2 raised to n by, yeah, 2 raised to L by L. Okay, so let's define L such that this 2 raised to L times L, 2 raised to L times L is more than T prime. In fact, not that. Let's fix it to be T prime. And 2 raised to L by L is this T which T is less than equal to 2 raised to L by L. Okay, so basically the motivation is that the upper bound you want to be T prime. So let's take 2L times L to be T prime, and the lower bound you want to be T. So let's take T behind 2 raised to L by L, and so which means what is L now? So we can take L to be so this L will be something like log T prime. You can take it to be log T prime by. Okay, so let me correct one thing here. Let me weaken it just slightly. Let me make it log square. Okay, so let's say T prime is bigger than Tn times log square Tn. And now I'll complete the proof. So what we want is an L which is roughly like log T. So let me fix L to be log T plus slightly more than that, because I want 2 raised to L by L to be bigger than big T, right? So I want slightly bigger, L to be slightly bigger than log T. And now you can just verify that we have T less than equal to 2 raised to L by L, T less than equal to 2 raised to L by L, less than equal to 2 raised to L times L less than equal to T prime. Okay, this 2 raised to L by L is roughly, you can check that it is just above T. You can check that this comes out to be T times log T by, then you are dividing by again by log T. So, this comes out to be theta T, and 2 raised to L times L comes out to be T times log square T. You can check that. And since we have assumed T prime is sufficiently bigger than T by this T times log square T amount, so there is enough space between T and T prime to actually fit this L. And once we have fit L between T and T prime, now you know that now you can invoke the points number 1 and 2. Okay, you can find the same, can find an FL is more than 2 raised to L by L size, that requires more than 2 raised to L by L size, yet it is computable in 2 raised to L times L. Okay, so that will separate size T from size T prime. So, by points one and 2, there exists an FL which is in size 2 raised to L times L, but not in size 2 raised to L by L, right, which means that size T is strictly smaller than size T prime. Okay, so we have been able to show that if T prime is sufficiently bigger than T, then the complexity classes, actually the circuits can compute more. Okay, so you can ask the question here, can this hierarchy theorem be improved? Okay, so how far do you need T and T prime to be? Can you improve this? Just like the time hierarchy theorem, we had a question. And yeah, so once we have this complexity class size T, and we have also proved the hierarchy theorem, we can now define something like polynomial time class P. Now we are ready to define a P analog. An analog of P. So, what will that be? So, unsurprisingly, it will just be the union over all polynomial sizes. Okay, but the name has an interesting notation. It's called P slash poly. Okay, so this is called P slash poly. And what is this? So these are the problems with poly-size circuit families. Solvable by poly-sized so these are decision problems that have poly-size circuits, and so immediately you can we can prove these properties, or we get these properties just by definition. That P is contained in P/poly. This needs some implementation, but at this level you can do it as an exercise. Any polynomial time Turing machine, step by step you can actually convert it into a circuit. You take basically n bit input x1 to xn, and whatever the Turing machine is doing, you can convert it as well into a circuit. Think of it as a silicon circuit implementing an algorithm for a fixed input stream, and by that you will be able to show that the circuit you get is poly-sized. It's basically bounded by the time number of steps. So P is contained in P/poly. But does it mean that we can use P/poly as practically solvable problems? Well, so surprisingly it has uncomputable problems also. So P/poly has uncomputable problems. Has an uncomputable problem. So let's quickly prove these two things. Maybe we'll do this next time. Thank you.